That's a strange thing. That is very strange. Why would having 4 roots at 5 indicate that there's no root at 8? Okay. Why? Do we know anything about g of x? Oh, okay, but. Number 10, the hardest problem on this entire competition. Given the polynomial, this polynomial. Oh, I'm scared of this question already. It's a polynomial. With integer coefficients, okay? And given also that there exist 4 distinct integers a, b, c, d such that they equal to 5. Show that there is no integer k such that it's equal to 8. That's a strange thing. It's a polynomial and it has 4 integers, distinct integers. That is very strange. Why would having 4 roots at 5 indicate that there's no root at 8? Okay. Why? There is no integer. Okay, so if you're an integer root, you must be of the form x minus a or k or b or whatever. Those are 4 roots at the whole thing equals to 5. Why? These are the 4 roots of f of x minus 5 is equal to these 4 roots times g of x. Do we know anything about g of x? We don't know if it has roots. We don't know if the roots are going to be integers or even real numbers, or it could be rational. Do we know anything? Well, f of x minus 5 has all integer coefficients because f of x has all integer coefficients, and then 5 is an integer. You just take 5 away from the constant term. So the constant term ends up being integer anyway. These things all have integer coefficients. Do we know if that's true for g? Well, we know the leading coefficient is 1, and the degree is m minus 4, because this is x to the n, like that. Does g of x have all integer coefficients? Assume g of x has a non-integer coefficient. What letter should we give it? C, M's, G's, K's? No, there's a K already. C's then. No. Has non-integer coefficients. Some terms. Highest degree. So if we write out g of x, it's going to be x to the power of m minus 4. Minus 4. We gotta start with minus 4 and then minus I. Plus c1 x to the n minus 5 plus c2 x to the minus 6 plus, and then all of these are integer coefficients until this one, m minus 4 minus I. These are integer coefficients, and that's the first non-integer. Plus, what's the last one? c m minus 4 is the constant term. We know that there are integer coefficients terms leading because the first term has coefficient 1. And so there's at least one term with integer coefficients in front of the non-integer one. Let's say we just take one of these binomials, x minus a times g of x. In the expansion, this is going to have as the term, x is going to multiply by this non-integer one. So c I x to the m minus 3 minus I. And this is going to multiply to the term left to it, which is 1 degree higher. A is going to multiply to that. I minus 1 x to the n minus 3 minus I. And these are the only terms in the expansion with degree m minus 3 minus I. So we're going to add them. A and c I minus 1 are both integers. Oh, let's not call it g of x because we're not multiplying all 4. Let's call it h of x. And we're not going to use, minus 3 minus 1, and this is minus 1. Therefore, when we combine like terms, this thing, x minus a times h of x, has the term ACI minus 1 plus CI, x to the power of m minus 1 minus I. And this is not an integer. All of this to say, whenever we divide out one of these factors, if we start out with an integer polynomial, we're going to end up with an integer coefficient polynomial. Therefore, g of x has all integer coefficients. Because if it doesn't, then when we multiply, we're going to end up with a non-integer coefficient. So we have that conclusion, and we have this. Let's rewrite this. I don't have space. There's no integers such that it's going to be equal to 8. When we plug it in here, if we plug in k here, let's just try. And this is k. This is going to be 8. This is 8. 8 minus 5, so 3. This is our integer coefficient, so this is going to be an integer. And this is going to be an integer. They're all integers. Now the integer factors of 3 is plus or minus 3 and plus or minus 1. But we can have only one of these, and 2 or 4 or 6, we can have 6. 1, 2, 3, 4, 5. Yeah, 5. 2 or 4 of these. Oh, okay, but. A, B, C, and D are all distinct. So k minus A, k minus B, I'll write it here. K minus C, k minus D are also all distinct. But the choices of factors are only one of these and 2 of these, plus or minus. But we have only 3 distinct choices of factors for 3. Now, if I were writing a formal proof, I'd have to start by something along the lines of assuming there's a k that exists that makes f of x equal to 8. But I didn't. Therefore, there must not exist a k for which, not the switch, not the witch hunt witch, for which f of k equals to 8. And we're done. Slightly more involved than the other questions, I guess. Pretty good for number 10. Accessibility, you will need to be pretty familiar with polynomial division, long division, or no, at least the expansion. Grade 11-ish. Originality, this is pretty smart. 2 out of 3. Explorability. I wonder if it's true that if you have integer coefficients for a polynomial and you divide by another polynomial with integer coefficients, that you're always going to end up with an integer coefficient polynomial. Like, what if there's a remainder? Does that change things? What if it's not a binomial? Does that change things? Okay. Do I like this question? It did make me think a bit, especially with the integer coefficient bit. Yeah, I like it. 7 out of 10. And that's it. That's the hardest question on the 1970 Canadian Math Olympiad. Ta-da! I solved them all.